Hi everyone, and welcome to the 2020 World of Physics at WOMAD. I'm Ellie.
And I'm Toby.
And in our session, we're going to explore colloids with some of our friends at Badminton School. Colloids are very common types of mixtures, but they're not studied very often while you're in the classroom. We hope that you will follow along with some of these demonstrations and hopefully learn some science along the way.
If you're going to have fun with colloids, please make sure that you get permission first, as things can get a bit messy. You should also have someone around to supervise you if you are still at school.
Hi everyone, I'm Ellie. In this segment, we're going to tell you a bit about colloids and where you can find them. There are 3 different types of mixtures you commonly come across: solutions, suspensions, and colloids. In a solution, you have a solute dissolved in a solvent, and this type of mixture is very difficult to separate because the particles are similar size to the atoms and mixed up. A suspension is where you have a mixture of insoluble particles that settle out over time. Colloids are formed when you have a uniform mixture of particles evenly spread out throughout another substance. There are 2 special terms we need to use at this point. In the colloid, there will be one substance which you could travel through from one side of its container to the other, without ever needing to move into the other substance. This is called the continuous phase. The substance which is spread through the continuous phase is called the dispersed phase. Typically, the particles in the dispersed phase of a colloid have a diameter between 1 nanometer and 1000 nanometers. The particles do not settle out over time because they are so small that other forces in the medium have more effect than gravity, so the dispersed particles remain suspended. There are 8 types of colloid. You can't have one made of 2 separate gases, as they will always mix fully. Having finely mixed particles of 2 different phases can lead to changes in properties. Pumice is a rock with such a low density that it will float, while gels flow like a liquid, but the particles can be harder to separate than some soft solids. Here is a matrix that shows the different types of colloid and their common names. You will find some of them quite familiar. For example, if you have a gas dispersed in a liquid, you can make a foam, and whipped cream would be an example of this. While if you have a liquid dispersed in a gas, you have a liquid aerosol, like mist. Smoke is an example of a solid aerosol, while pumice stone is at least close to being an example of a solid foam, as it is a rock with so many tiny gas bubbles trapped inside that it will float in water. Gels are examples of when you have a liquid colloidally dispersed in a solid continuous phase. Jams and jellies are a good example of this. As we move through this phase of the talk, we will have a look at some common and less common colloids.
Hi, I'm Lucia and I will be showing you how easy it is to make your own emulsion. You will need the following ingredients. Do experiment with your own ratios: oil, vinegar, mustard powder, a shaker, and optional salt, pepper, garlic and chilli. Oil and water are completely immiscible. Water is polar, meaning it has charged regions, while oil is non-polar. Particles of oil prefer to stick to other oil particles, and, likewise, water particles prefer to stick together. If you shake vigorously, they will mix together for a moment, but quickly small droplets of each liquid grow as the less dense oil floats to the surface. Mustard powder contains some unusual molecules that come from the coatings of mustard seeds. They are hydrophobic at one end, making that end good at sticking to oil. At the other end, these molecules are hydrophilic, meaning that they love sticking to water. If you take some mustard powder and mix it with vinegar, which is a mixture of water and ethanoic acid, which is also polar, then the water and vinegar will form tiny droplets coated in mustard. Now mix this into oil, and the droplets are small enough to stay suspended. You have formed an emulsion that will help you enjoy several portions of your 5 a day. The mustard acts as an emulsifying agent. It both stops the dispersed droplets from sticking together and helps them form a stable interface with the oil by partially dissolving in it. I hope you enjoyed that demonstration and that you will give it a go yourself.
A ferrofluid is made by suspending solid particles of iron oxide in oil. To stop the particles sticking together permanently, they are covered in a thin coating of oleic acid, a component of many vegetable oils. In the absence of an external magnetic field, van der Waals forces from the coating stop the particles from clumping together. As the particles of iron oxide are tens to hundreds of nanometers across, they form the dispersed phase in a sol. Van der Waals forces are stronger than magnetic forces from the particles. In the presence of a strong magnetic field, the iron oxide particles line up and form spikes in a complicated three-way interaction between gravity, magnetism, and surface tension. And we're going to explore some common and perhaps slightly less common colloids.
Let's start with milk. Milk is a colloid and we can use it to show a common property of many colloids.
This delicious and nutritious drink is an example of an emulsion.
Liquid butter fat is dispersed through a continuous phase made out of a water-based solution of sugars and proteins.
You can use milk to show the Tyndall effect, which happens in colloids that do not have a solid continuous phase.
If you take a glass of water and shine a laser through it, you cannot see the beam.
Light travels in a straight line, and therefore you cannot see the light's passage through the water.
If we add just a few drops of milk, the beam becomes visible. The dispersed phase forms droplets of the order of a few hundred nanometers across, suspended in the much smaller particles of the continuous phase.
As the drops of liquid butter fat are similar in size to the wavelength of visible light, the light is scattered by the droplets and some end up travelling straight into your eye. A similar effect, called Rayleigh scattering, causes the sky to be blue, although Rayleigh scattering is much weaker.
Hi everyone, welcome to the DIY section of making slime. Are you all ready to follow along? So the most important ingredients are 45 ml of PVA glue, 3 ml of contact lens solution, and 2 grams of baking soda. Some optional ingredients will be a few drops of food coloring, which can make your slime more colorful, 2 ml of shaving foam, which will give your slime a fluffier texture, and finally about 4 ml of soap, which will make your slime have a pleasant smell. And utensils you will need include mixing bowl and a spatula. Slime is made from polymers. A polymer is made of a very long chains of molecules of monomers bonded together. The PVA glue we use is a suspension of polymers. These are long chains of acetylethyl molecules, which have hydroxide groups on their chains. And this will be very important later. Polymers are like spaghetti, where the chains slide past one another and keeps the glue flowing. And that's the reason why PVA glue is so viscous. The slime is made of lots of these long polymers joined together. But there's a bit more to it, and we'll come to it later after making the first version of slime. When making slime, parents must supervise their younger children, as these ingredients are usually considered as safe. They should not be eaten as it can cause tummy problems. First, pour 45 ml of glue into your mixing bowl. After that, add 2 grams of baking soda and stir vigorously until it is mixed really well. Add 3 ml of contact lens solution and your slime will start to gradually form when you mix. If your slime is too liquidy, add more contact lens solution, as it will make it more stiff. However, be careful on how much contact lens solution you add and how quickly you do it, because too much contact lens solution can make your slime too firm. 2 liquids are combined to make classic slime: PVA glue and borax in solution. Dissolving borax in water involves some complicated chemistry. However, for our purposes, our important part is when you either have borax dissolved in water or boric acid, tetraboric ions are present. These ions found in the contact lens solution form weak hydrogen bonds with the hydroxide group in the polymer and linking them together, which is known as cross-link. This needs an alkaline environment, so the baking soda activates the process with a pH of 7.2. The PVA glue no longer flows freely because the molecules in the slime have become weakly joined and the texture changes. The cross-link of polymer chains become too large to remain suspended and form solid phase of gel. Water is trapped by the chains, so the slime is soft and flexible like other gels. The consistency of a slime is controlled by the ratio of glue to borax. If you have excess glue, the number of cross-links is limited. Therefore, you will make a very fluid slime. If more borax solution is added, you make a stiff slime because it will form more cross-links and the chain will have less freedom to move. Here is an example of a very stiff slime. To make fluffier slime, we use the same recipe. However, some shaving foam is needed to be added to the PVA glue before mixing in the contact lens solution. Here I am using 2 ml of foam, but adding more will make your slime fluffier. However, adding too much of the foam will make your slime wet and gloopy. Add a few drops of food coloring now is what you want to make your slime colorful. But be careful not to add too much, because it will be too dark and you will spend days getting it off your hands. Air makes the slime fluffier because it contains air bubbles. Foam is a colloid. Its dispersed phase is air, and the continuous phase is liquid. The new slime is basically a really complex colloid because it contains of 2 colloids, which is the original colloid of the original gel and the new additional foam. To keep your lime stretchy and healthy, it is really important that you don't break the slime fully, like this, because this will break the crosslinks between the slime and the polymer chains, permanently damaging it and changing the texture of it. Making crosslinks is actually very important in chemistry, especially you find them in car tires. Soft natural rubber is heated with sulfur, and the resulting crosslink makes a strong, durable, and less sticky substance. Thank you so much for listening.
Thank you for watching What a State by Badminton School's Science Outreach Team.
We hope you enjoyed the demonstrations and that you will have a go at some yourselves.
Many thanks to Linda Ross, Connie Potter,
Roger Jones and Miranda Addy, and all of the WOMAD World of Physics 2020 team for inviting us to be part of this event. We hope you enjoy the rest of the programme.